please. So today we are going to do section 16.1. Up until this point, we've been doing derivatives of functions of several variables, and now we'll talk about integrals. So introduction to integrals of functions of several variables. Okay. So our functions, functions of several variables, they are going to be single. We get a single variable output from a multivariable input, right? As is the case, will be the case in all of this middle section. Okay. So here's the idea, right? You have some function, and it is on some rectangle in R2. A positive continuous function. Okay, and by this thing here, I mean that you take the interval AB and you cross it against the interval CD, right? And you get this rectangle. Okay, you get this rectangle, and to each point on the rectangle, to each point in the rectangle, you associate some value in R. Okay, right, so to every point xy, right? To every point xy that's in here, you associate some value, right? F of xy. Right. Of course, x lies between A and B, and y lies between C and D, inclusive. Okay. So pictorially, sort of graphically, we've got A, B, C, D here. If you draw the graph of this, right, then here's your domain again. We've laid the domain down flat, right? And then above the domain, you have some sort of, you have the graph of your function floating above it, right? Maybe like this. You have some sort of carpet, floating above your domain. Right? So this is the graph. Right? This is the graph of your function. Okay, everybody on the right page? Okay, and so the question is, how just like the question in Calc 1, right? Question in Calc 1, of course, is that you have some integral, and then you have some function above it, and you're interested in the area. You're interested in the area under the graph of that function, right? So y equals fx. Here we've got z equals fy, and you're wondering at the volume of the solid that's underneath the surface. Okay, so here you make some sort of solid, right? By taking this thing as the roof of your house, right? And then looking at that solid block, right? With that roof, and you're wondering what the volume of the solid is. So the question is, what's the volume of the solid? What's the volume of the solid underneath the graph of F? Okay. Everyone all right? Yes? No? Lily, are you okay? Yes, thank you. Okay, so let's recall how we did it in one variable calculus, right? Somebody gave you something like this and said, what's the area under that curve, and how did we do it? Do you remember? How did you do it?
Took the definite integral.
Took the definite integral. Well, what's the definite integral of this thing? I don't know. But what does the definite integral give you? Or like the area underneath the curve? Yeah. But so suppose your function doesn't have an antiderivative or something like that, or so it's true, right? We have this thing which gives you the area, right? But how did we get that area?
Riemann sums.
Riemann sums, yeah. Riemann sums. by Riemann sums. So what's the idea of Riemann sums? What's the idea of Riemann sums, Lily?
Draw little rectangles and
That's right. That's right. So you partition the base into equal intervals, equal subintervals, right? So when you partition AB into say n subintervals, I1 through In, right? And subintervals of equal length. Okay, and then, right, after you do that, what do you do? How did you guys do it? There are a couple ways to do it, so I'm kind of curious. I'm not that curious, but tell me what you did.
Wasn't there like right hand, left hand, midpoint?
Okay, so you could, one way is to take the right-hand point of every subinterval and then evaluate there, right? Another way is to take left-hand intervals. Another way to take the midpoint. Other ways, people? Other ways that people did it? There's one way where you look over the interval and you find the lowest value, and you also look for the highest values. And then another way is just to take a random point. Okay. So in any case, pick sample points, one way or the other, right? Xi star in the ith interval. So in each interval, choose a single sample point. Right. So we're going to pick these sample points. They call it xi. Right. So here is my I1, I2, I3, I4, I5. Right. And I'm going to pick sample points sort of however I feel like. This is going to be my x1 star, x2 star, x3 star, x4 star, x5 star. Okay. And then what do you do? What do you do with those sample points? You
use them as the height to calculate the area of the rectangle.
Right. So you calculate the areas of the rectangles. So you say, I'm going to take that height, right? I'm going to take the value of f, at that height, and I'm going to multiply it by the width of the base, right? By the width of the base, where delta x is b minus a over n, right? The length of the entire interval divided into n parts. Right? We made them all the same length. Right? So that's the area of the ith rectangle you make by taking at this height, taking a rectangle of this height. So you take the thing here, evaluate the function, and then make a rectangle of that height. Right? And then you sum all those things together over I. Right? And that thing is called a Riemann sum. Right? So Riemann sum approximating the area. Right? And then you let n go to infinity. Okay, so you do this, you basically do this repeatedly as n goes to infinity. So, right, so take the limit of such sums as n goes to infinity. Okay, so for every n, right, you partition, you select, you create an approximation. So for every n, you get a different approximation, right? Let's call this thing a sub n, say, the nth approximation. Take the limit of the a sub n as n goes to infinity, and that gives you some number, right? Right. So for integrable functions, this limit exists independently of choice of sample points. We call the limit the integral of f from a to b. So this is the review of one variable integrals. Right. And then later on it turned out that you have these things, the fundamental theorem of calculus and stuff that allows you to calculate these integrals without using Riemann sums, right? Because using Riemann sums to calculate integrals is a pain, and so fortunately for us, we have this thing called fundamental theorem of calculus. Okay. So, but that's sort of how we're going to go through. How are we going to find the volume here? We're going to do exactly the same thing. Okay. So we're going to partition this rectangle into subrectangles, right? And you just play the same game. So I'm going to basically write the same thing down, just in a slightly generalized fashion. So we do the same thing. We do the same thing in higher dimensions. Okay, so here we go. You have some function on the rectangle AB cross CD. Okay. Is everyone comfortable with this notation here? AB cross CD. Right? It's just a rectangle. You take the interval AB, cross against the interval CD. Right. If I'm talking about, say, 1, 2 cross 3, 7, it's this rectangle here. So here's what we do: partition AB into n equals subintervals, right? AB and CD both each into n equals subintervals, right? So the ABs I'm going to partition into I1 through IN. The CDs I'm going to partition into J1 through JN, right? So intervals, subintervals of equal length. So here I'm going to call this delta x, delta y, right? Delta x is going to be b minus a over n. Delta y is going to be b minus c over n. Right? And so you see in the picture what happens, right? I've taken 1, 2, and I partitioned it into, say, 4 parts. I partitioned this guy into 4 parts. So equal subintervals, right? And then I've got I1, I2, I3, I4, J1, J2, J3, J4. And I notice that ABCD then is the same thing as the union of the I across the JJs as we go over all I and J. Right. If I look at all these combinations, right, I1 cross J1, I1 cross J2, I1 cross J3, I1 cross J4, I2 cross J1, I2 cross J2, I2 cross J3, I2 cross J4, etc. I see that I cover this thing up with these subrectangles, right? So these guys are these subrectangles. We've taken our rectangle and partitioned it into subrectangles. Okay. So nothing new. It's just notation, basically, right? Just a matter of nice choice of notation. Okay. Now we pick sample points. Pick sample points. Let's call them Cij star. That's Cij star is going to be in II sub jj. So this is a Xi. It doesn't matter. You can just make some sort of squiggle.
What does it mean?
Xi. Like it's one of the Greek letters. Like X, it's an X. It's the forerunner of the X, I think. Okay. So you pick sample points. This is going to be somebody in X in, right? So Xi11 is some point in here. Xi12, Xi13, Xi14, etc., etc. Right? So your picture is that you have, you've divided your thing into subrectangles, right? And in each subrectangle you pick some sample point. Right? Each subrectangle you pick some sample point, right? And you just play the same game, right? At each sample point, you take that as the height of some parallelepiped. So instead of saying rectangle, it's not the area of a rectangle, but rather the volume of the parallelepiped. So then, summation I equals 1 to n, j equals 1 to n of f evaluated, actually that's at Fij star times delta x delta y, right? This is the area of the base, right? Area of the base times the height. You get the volume of the parallelepiped, and you sum over all parallelepipeds. Right? It's called a Riemann sum. Of f on AB plus CD. So the idea is nothing new. What is slightly new is the notation. So just get familiar with the notation, because we'll need the notation. The only thing that I think is maybe a little bit misleading is that this Xi really stands for some x comma y, right? This is a point on the plane, right? It's really x, y. I should probably put a vector sign over it. But I'll probably forget to. But other than that, I think it should be clear. And then, just as before, if this limit exists, if the limit as n goes to infinity exists independently of choice of sample point, then we define the definite integral f xy dx dy to be that limit. And say f is integrable on that rectangle. Okay, so let me call this rectangle R. Let me call the rectangle R. This is the definite integral of f on R. Yeah. Fine.
Are there bounds on the integral signs, like from A to B or something?
Not right now.
Okay.
They will be later. But right now we're just going to say the integral over this rectangle.
Oh.
Yeah. In fact, it's probably better to write it like this. But I'm going to leave it like this. No, sorry. In fact, in my notes, I have it like this. So I'm gonna leave it like that. Yeah. And in fact, it would probably be even more natural to leave off this double integral, right? So this is actually sort of more logical, right? You're taking the integral against the area over this rectangle. Okay. We use the double integral because later we'll see that you can calculate these integrals as iterated single integrals. So later on we'll see that in fact this integral is equal to an integral of an integral. Okay, that's what we'll see later. And that's why we use the double integral here. But in some sense, it's confusing. Like, why are there two integrals? So let me make one remark. Continuous functions have, if your function is continuous, then it's integrable. So f continuous, then f is integrable. So if your function is continuous, then this limit is going to occur. This limit is going to exist. Okay. So right. So, as how do you? The question, of course, is given a function, how do you find the integral, right? Unfortunately for us, we're basically going to, give you the technique so that you don't have to do Riemann sums. Okay. So here's how you do it. Here's the method. How does one find this limit? How does one determine this limit? And the answer is, here's one trick. Someone iterated integrals. That is to say, integrating along on slices. Okay. So here's the theorem that allows us to do the trick. Okay. All tricks have to be founded on some sort of knowledge. And here's the piece of knowledge that gives us the trick. Suppose you have your function and it's on a rectangle. If f is continuous, then this integral exists. And 2, the integral can be calculated. As follows. As the integral, first you take the integral of f(xy) with respect to y between c and d, and then you integrate the result of that over x from a to b, or you do the opposite, or you take the integral over x first, and then y. let me do an example. So let's say r is 0 pi cross 0 pi. And somebody asks you to integrate 0 cosine y over 0 pi 0 pi. So you say, okay, well, by my theorem, this thing is continuous, right? This thing is continuous, so I can integrate this as an iteration of single integrals, right? So I get right, this double integral, which I would have to go through the Riemann sum to calculate, can actually be calculated as an iterated single integral. Okay, so right, so you say, okay, I'm going to integrate with respect to x first, right? And there's one thing you notice that look, cosine y is not dependent on x, right? So with respect to x, this is constant, right? Cosine y is fixed with respect to x, right? As x moves, the cosine y doesn't change. So I'm gonna that's a constant, so I can pull it out. So this is the same thing as the integral here of cosine y integral x dx. Okay. Yeah, Melissa.
I'm a little confused. What
Yeah.
part's like what they would give you? Or what are you answering? What's like the question? that
This is
you're
the question. This is the question.
So that's all given.
What's this integral?
Okay.
Yeah. So, yeah, what we're showing is that you can calculate these double integrals by using this formula, which says that a double integral can be realized as just iterated single integrals. So somebody gives you a double integral, and you say, well, okay, I'm not afraid of this. All I have to do is multiple single integrals, right? So I'm going to integrate. I integrate this thing first, right? And what's the integral? What's the integral of that? Well, I'm going to get, of course, x squared over 2. Right, I get x squared over 2 evaluated between pi and 0. Right. So I get pi squared over 2. Right, minus 0. And then I have this other integral, which is cosine y dy between 0 and pi. And what happens when you integrate that? You get sine.
Sine 0.
So you get sine pi minus sine 0, which is to say 0. Right? So you get sine y. This y goes from 0 to pi, and that turns out to be 0. Okay. So pictorially, what's going on here? Here is 0 pi, 0 pi, 0 pi, 0 pi. Right, so here's the domain, right? And then you have x times the cosine, right? Well, the cosine is going to be like, let's say we're at 1. Okay, so if we're at 1, then the cosine of 0 is 1, and then it goes like this, right? Right? It'll go like this, right? And then you're taking that cosine function and multiplying it by x. Oops, sorry. Let me call this x. Let me call this x and this y, because that's how I'm drawing it. Okay. Right. So as y goes from 0 to pi, the cosine goes like this. everyone with me? Okay. Right, and then we're multiplying this thing by x, so you get these bigger and bigger guys, right? Taller and taller guys as you go along. Drawing is awful, but right, like this. Like this. Okay. Right. And so what we do is we say, okay, we're going to integrate that thing by holding the y's fixed, fixed, and integrating along the x's. Okay. So the picture is that we take a slice here, and then we take the integral of that thing, right? We take the integral of that thing, and then we integrate that thing from along the y's afterwards. Okay. Let me draw a better picture. So here's the idea of the theorem. Okay. Right, you have your domain like this, and then above it you have again your some sort of carpet. Right? So here, something like this. Okay, and you're wondering what the volume of this thing is. Okay, so what you do is you say, okay, I'm going to integrate. Let's say we do it this way. I'm going to hold the x still, and I'm going to integrate along the y. Okay, I integrate along the y, and for every y, I get some sort of for every x, I get some sort of function of x. I get it I fix an x and I slice it through, and I get some sort of area, right? And that area depends on x, right? As x changes, that area changes, right? That's this thing here. Right. A of x, right? A of x is going to be, you integrate you fix the x, right? You fix the x, and you integrate along the y only, right? You integrate along the y only, and you get this thing, which is dependent on x, right? It's some function of x. Okay, and then you're going to integrate those areas over x, right? And you sum all of those areas together and you get the volume. Okay. So you take slices, you hold the x's still, you get the areas of slices, and then you integrate the areas of the slices along the x over all x, and that gives you the volume. Okay. So that's what this theorem says is possible to do. That is, you can calculate volumes by integrating the area function against the second variable. Okay. Okay. Take 1 minute and do it in the opposite order. somebody next to you and say what you get. Of course you got 0.
Here's x out as a constant, you take the cosine y, sine y, and then pi is 0 pi, 0, 0 out, roll that, 0 times x squared.
Okay. So what do you do? Right, you're going to integrate this thing with respect to y first, rather than x. Right, and so what happens?
0 times the integral of.
You get 0. Right, so this x is constant. You pull it out. Right, so you get the integral x blah blah 0 pi cosine y dy dx. Right. So then you get the integral of this thing, but you know what that is. It's going to be sine y between 0 and pi, right? And so you get the integral of this is 0, right? This becomes 0. So you get the integral of 0, which is to say 0. Okay. Any questions? Any questions? Straightforward. Here's another one. R is the rectangle given by this, and you are going to integrate over R x cosine xy dA. Okay, give it a try. So the main question is, which variable are you going to integrate with respect to first? Okay, turn to somebody next to you and say what you're doing. Can you talk to me?
This is a constant or something like that, but then change it would be sine x y times 1 over x. The value is from 0 to 5. So would that only
In this
count?
case equals dy because
So
we
what
did
is
dy in order to integrate cosine of a constant. I think that was my calculus. So I use my x, I vary y first, and so I get the integral of cosine, which is just regular sine, and then x goes away because it's used to integrate. And so then I have integral of sine xy
Well, don't you have to like account for something else?
Yeah, I use this. I use x as the dy. So I had to integrate for y first. Does that make sense? Because x is a constant. I think that makes sense.
I'm still with you.
Okay, so who would like to say how to do this? Or what variable did you integrate with respect to first? Y. Okay, because it's impossible if you do x. Okay, that's a good reason to use y. Right, so x is going from 0 to 1, y is going from 0 to point. Okay. Okay, so you integrate with respect to y, and what do you get?
Sine x1.
Sine x1. Right, between 0 and 1. Right, because the derivative of sine xy with respect to y is going to be x cosine x1. Right, this x is a constant.
Right, so just
Right, so when you differentiate sine xy with respect to this, right, it's like you have an a here, right, some constant here. The derivative of this is going to be cosine of ay times the derivative of the interior, right, let's just say a, right, by the chain rule. Okay, so it's just recognizing that this is a constant and then using the chain rule. Okay. So from there, right, we're integrating between 0 and 1, this thing, right, so we get sine, that's y ranges from 0. So we get sine pi x minus sine 0 as x ranges between 0 and 1. And what do you get? Sine 0 is just 0, right? Here we get sine pi x, right? So what's the integral of that?
Cosine pi x.
Negative.
1 over pi.
Thank you. Negative 1 over pi cosine pi x, again by the chain rule. Because when you differentiate cosine pi x, you're going to get negative sine pi x times pi. Right. The derivative of cosine pi x is negative sine pi x times pi. Right. So we need a negative 1 over pi to make this right. And you evaluate that between 0 and 1. You get negative 1 over pi cosine of cosine pi minus cosine plus 1 over pi cosine of 0. Right. Which is 0, right? Which is against 0. Right, because cosine of pi and cosine of 0 are both. Oh wait, no. This is negative 1.
So it
Sorry,
becomes
this is negative.
2
This is positive.
pi.
Right, 2 over pi. Sorry. 2 over pi. Okay, so pretty straightforward, right? Double area integrals are just iterated single, double integrals are just iterated single integrals. I should say that one really does need the continuity to change the order. Like for us, as long as it's continuous, you can integrate with respect to y first and then x, or x first and then y. But if it's not continuous, actually all bets are off. If you integrate in one direction, you'll get one answer. If you integrate in the other direction, you'll get another answer. Okay, so continuity is actually necessary.